GW have a field?
I think they only have a soccer field.
Oh. Are you gonna do like club soccer there?
Club or injury.
So 12.1, we're going to talk about this thing called Chi Square Test for Goodness of Fit, which is a very funny name to me, but as always, statisticians and mathematicians aren't ones for flowery language. They just give them the name that is the simplest and describes exactly what's going on. So what we're going to talk about is we already know how to run a test if we're trying to see if a claimed proportion is true. But now we're going to look at what if we're trying to look at multiple proportions at once. So in this case, specifically, Skittles claims that they have a uniform distribution of color. And it didn't used to be uniform, apparently. I looked into the history of this a little bit because machines used to package them by weight. And so I guess there were slight differences in the color coding by weight. And so the distribution wasn't uniform, but then they started packaging them by color, and now it's claimed that there's a uniform distribution. So the colors we have are what? We got red, yellow, green, orange, and purple. So 5 colors, which means if it's uniform, each one of them should constitute 20% of the package, right? 20% for each color. So what we want to do is test and see if that distribution is correct. So now we're testing multiple proportions at once, not just a single proportion. And that's what we're going to use this thing called a chi-square test for goodness of fit. So the claimed color distribution of Skittles lentils is uniform. That's what they're called, Skittles lentils.
What?
There's no such thing as one Skittle. It's always plural. And so a single piece of candy is called a Skittles lentil.
Like the bean? Like
Yeah, the lentil, Katie.
okay, so that means it looks and tastes kind of like a bean.
Yes, that is one Skittles lentil.
I wish I could go back 30 seconds. Yeah, no, I know that.
All right, so here's how the null hypothesis looks. You can state these both symbolically or verbally. It's a little bit easier to state verbally, and I'll show you why. But the null hypothesis is basically that their claim is correct. So Skittles color distribution is uniform. And then the alternative would just be Skittles color distribution is not uniform. And we're going to do this at alpha equals 0.05. And so anytime, like the logic of the significance test stays the exact same as the significance tests we were running before, which is, okay, we assume that the null hypothesis is true. We go out into the real world, we take a sample, we look, how far does our sample differ from the null hypothesis? If it differs not that far, then we go, all right, I think the null hypothesis is maybe true, and it just differs a little bit because of variability from sample to sample. Or if our sample differs from the null hypothesis by a lot, we go, wow, this is evidence that the null hypothesis isn't true and that the alternative hypothesis is true, right? And the threshold for that evidence is the 0.05 level. If the probability is less than that we were to get our sample, if the null hypothesis is true, then we have significant evidence for the alternative. If the probability is not less than 0.05, then we fail to have significant evidence for the alternative, right? All right. Symbolically, what this would look like is this. you would just have to state each proportion. So I would go, what are the colors? Okay, so proportion red is 0.2. Proportion yellow is 0.2. Proportion green is 0.2. Thank you. Proportion orange is 0.2 and proportion purple is 0.2. Now the alternative would be that at least one of those is not 0.2. It is not that all of them are not 0.2. Does that make sense? It's just that at least one is not 0.2. And in fact, if we want to get technical, if one of them is not 0.2, then two of them have to be not 0.2, right? But I want to be clear, and this is something that they state caution for. You don't want to state the alternative hypothesis in a way that suggests every proportion has to be wrong, because that doesn't have to be the case. It's just that one or more of them have to be wrong, which is why it's a little easier just to state these verbally. Just state this color distribution is uniform or it's not. Easy enough, right? All right. Now, I need to know the total count for us. So go ahead. All right, so let's do observed and expected. Let's do, so we got red, yellow, green, orange, and purple. All right, so if we have 118 Skittles lentils, how many would we expect to be red if the null hypothesis is true? How did you come up with that, Sam? So basically, we would expect 20% of them to be red, right? In fact, we would expect 20% of them to be each color. So our expected counts for each color category is going to be 23.6, which is just 0.2 times our total sample size. All right, but we want to get the observed counts as well. So I need you guys to go through for me and count first reds. 2 plus 5, Riley. Ooh. All right, so we got 31 red. Yellows? All right, 3 plus 1 plus 3. None? Plus 0 plus 3 plus 5. 15. Green? 4 plus 2 plus 3 plus 4 plus 5 plus 7. 25. Orange? 16. And then purple.
9? That sucks.
31. So let me just make sure that we had 31 plus 16 plus 25.
I love yellow.
What?
I like red.
Yeah, red is the best flavor of every candy, right?
No. I like the, I just like, well, I don't like cherry flavor.
All right, so we can see that there's a clear difference between the observed and the expected counts, but so what we want to figure out is that difference statistically significant? Meaning, could it just be due to random chance and variability, or is there enough of a difference to say, hey, I think this is evidence for the alternative hypothesis, meaning that the distribution is actually not uniform, right? So what we need to be able to do is condense this down to a single number. And that's called the Chi Square Test Statistic. And here's how we're going to do that. The Chi Square Test Statistic is computed like this. What does sigma mean? Add. So we're going to take each observed count. We're going to subtract its corresponding expected count. We'll square it, and then we'll divide by the expected count. And then once we do that, we'll add all those values up, and that'll give us our single chi-squared test statistic. Now, the thing I want you to think about is if, let's say our sample was exactly what was expected, how much of a difference would there be observed minus expected? 0. So the closer to 0 your chi-square test statistic is, the less evidence you will have for your alternative hypothesis. The bigger your chi-square statistic is, the more evidence you'll have for your alternative hypothesis, right? So let's figure out what ours is. We'll do this in our calculator. And what I want you to do is just go to your calculator, and we're going to enter in list 1 your observed counts, and then in list 2 our expected counts. So list 1, list 2. We'll go stat, edit. Just going to clear out anything in there. Here's what we had. We had 31, 15, 25, 16, and 31. And our expected counts should all be 23.6. Great. So we're sort of going to do a hand calculation of our first p-value for the chi-squared test, and then I'll show you. Your calculator can actually run the whole thing for you. But list 3, here's where I'm going to do the individual contributions to my chi-squared test statistic. So I'm basically going to tell list 3 to do this formula here. I'm going to tell it to do just this part of the formula, the observed minus expected divided by expected. All right? So we're going to highlight list 3. We're going to open parentheses. We're going to go list 1, which is observed counts, minus list 2, which is expected counts. Close our parentheses. We'll go ahead and square that. And then we'll divide by list 2. There we go. So these are the individual contributions to our chi-square test statistic. And then we just want to add those up to get our single chi-square test statistic. So go ahead and quit to the main screen. And we're going to go to our list menu, which is second stat. Go ahead and scroll all the way over to math and choose sum. So that's the 5th option. And we're just going to add up list 3. There we go. So chi is just basically the Greek letter X, and it just looks like a fancy X. So like that. So our chi-square test statistic is 10.31. So big, pretty far away from 0. Remember, the closer to 0, the less difference there is in your observed and your expected counts. But is this far enough for us to consider it statistically significant? So before I talk about that, let's go into what a chi-square distribution looks like. All right, so a chi-square distribution is defined by a density curve that takes only non-negative values, right? That should make sense because we said, at best, if your observed counts are the exact same as your expected counts, then what's your chi-square going to be? 0. But other than that, it's going to be positive. So it's a right-skewed distribution, and the shape depends on degrees of freedom, which is still sample size minus 1. Okay? Your p-value is the area to the right of your chi-square test statistic. So ours is 10. So depending on which distribution we're looking at, our p-value is going to be the area to the right of that. And by p-value, I mean the value that you compare to your significance level, right? All right, so for our specific example, how many degrees of freedom do we have? Oh, I'm sorry. Did I say sample size minus 1? That is not correct. It is categories minus 1. I apologize. Not sample size. So it's number of categories minus 1. All right. So in our case, sorry, how many degrees of freedom do we have? Good. Okay. So we have 5 categories. So we have 4 degrees of freedom. And let's go ahead and run. So just like we had normal CDF when we wanted to find the area under a normal curve, there is a chi-squared CDF in your calculator. So that's what we're going to use. So we're going to use chi-squared CDF. And it's in the same place you would find normal CDF, which is your distribution menu. So we can go second, distribution. You can see it. It's the 8th option, right? You got your fancy X, CDF. It's going to ask for your lower boundary. This is your test statistic. So for us, that's 10.31. Your upper boundary is just going to be infinity. There's no infinity button on your calculator, so you'll use a bunch of 9s. And then your degrees of freedom. All right, so for us, let's go ahead and do 10.31. Upper 99999, degrees of freedom 4. And then this should give us back our p-value. P equals 0.036. Wow. So what are we going to conclude here? So I'll say at the sigma equals 0.05 level, do we reject or fail to reject? Wow, we reject H null in favor of HA. We have significant evidence that the color distribution of Skittles lentils is not uniform. I did it the whole time we did the experiment.
I'm not writing that.
All right, so what you want to do is a follow-up analysis after. If you have a significant result, oftentimes they'll ask you for a follow-up analysis because we compared multiple categories at this point. And like I said at the beginning, it's not necessarily the case that all the colors were out of whack, right? So we'll want to go back in and check which one was the most out of whack. Well, if we go up and look at our contributions to the Chi Square test statistic, which ones were the largest? Yeah, the second one, which was yellow, right? And orange. So we would say yellow and orange, right, were the most off proportion. It seems like, what was the middle one? Green was pretty on point. Pretty close to 0 in terms of its contribution, right? I'm not convinced, though. Because one thing I will say is that, like I said when I was reading up on it, I think that the color coding has different weights. So that means that as they're sitting here, the heavier ones, what you would expect to sift to the bottom. And I did not shake these up. Important science. All right. So let's talk about just a couple of technical details that we need to make sure we do when we're running a chi-square test for goodness of fit. And that is checking conditions. Here you go. Here are your conditions for performing a chi-square test for goodness of fit. Spoiler, they're the same as before. Random, 10%, large counts. But again, the large counts is going to be different than for a mean or for a proportion. Here's your large counts condition. Your expected counts need to be at least 5. That means you need to list out your expected counts. So we didn't check conditions on that last one. We'll do one all the way through. But before we do, let me show you. I said that you could do these full on in your calculator, and I'll real quick show you how to do that. All right. So if we wanted to run this fully in our calculator, we can. Let's just go to stat. Whoops. We'll go to stat tests. And it's the Chi Square GOF test. It's selection D. And then you're just going to tell it where your observed counts are. For us, that's in list 1. Where your expected counts are, that's in list 2. Your degrees of freedom, which is number of categories minus 1, so that's 4. And then you can just tell it to calculate, or you can tell it to also draw the distribution. I'll have it draw it out for us. There we go. So we see our right skewed distribution, gives us our test statistic 10.3, and it gives us our p-value 0.0356.
So in this one, you wouldn't have to do like L3 on
No, exactly. So we did it by hand the first time, but your calculator can handle doing that for you. All right, so let's do one all the way through. This is kind of an interesting one too, which is Does being born a certain time of year make you more likely to be a hockey player? A serial killer. I'm sure there are studies about that, but there are a bunch of studies that have to do with what time of year you're born and how likely you are to be like a successful business person or CEO. And it is statistically significant. A lot of it for sports depends on because kids born at a certain time of year, I can't remember, is it because I was an older kid for my grade, and they are more likely to excel at sports. Because when you're young, 8 or 9 months difference can make a huge difference in size. And then that can make a huge difference in how successful you are early on at sports. And so those kids tend to be more successful in sports in the long run versus kids who are young for their grade that just end up getting, walloped on early in life and then develop less of an interest in sports because maybe they're not as successful at them.
Although I think that's changing now, at least in soccer, because now they're moving towards year, like, so I'm in 02, so now I'm the youngest.
Right. So rather than like grade level, actually birth year, which makes sense. All right. So in his book Outlier, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest level of the game. Specifically because January 1st is the cutoff date for youth leagues in Canada, where many NHL players are born. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, success being judged by whether a player makes it to the NHL, a random sample of 80 NHL players from a recent season was selected, and their birthdays were recorded. This one-way table summarizes the data on birthdays for these 80 players. So we basically grouped them into 4 categories, right? To 4 quarters of the year: January through March, April through June, July through September, and October through December. Do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year? All right. So let's go ahead and run this one the full way through. Let's go with our null hypothesis. What should our null hypothesis be in this case? What do we want to assume? Yeah. I'm just going to say NHL birthdays are uniformly distributed. The alternative then? That's it. NHL birthdays are not uniformly distributed. We'll go with significance level of 0.05. All right, so that's our state. We stated our hypotheses. Let's check conditions. Plan. Random. They told us that it's a simple random sample. 10%. Our sample size is 80, so 80 times 10 is 100, and there are more than 800 NHL players. Are there? I don't know, but let's assume there are. You're not a huge hockey fan, Katie?
No. I'm sure
There's 903 NHL players.
that's a lot.
Yeah. Yeah, I don't know. All right, and then large counts. Here we have to list out our expected counts. So expected. All right, so if they're uniformly distributed, and we're only looking at this in terms of quarters of the year. So if we have 80 players and they're uniformly distributed, how many would we expect to be born in each quarter? 20. Those are all greater than 5. That's our large counts condition, so we're good to go, right? All right. So we want to run a chi squared goodness of fit test. And we'll just run that in our calculator and we'll go ahead and write down the test statistic, the chi-square test statistic, and we'll write down the p-value. All right, so list 1 is going to be our observed counts, which was quarter 1 was 32, quarter 2 was 20, quarter 3 was 16, and quarter 4 was 12. And then list 2, we want our expected counts, which we would have expected them to all be 20 if it was a uniform distribution. And then like Katie pointed out, we don't have to do the list 3 thing here. We can just let our calculator do that heavy lifting for us. So we'll go to stat, we'll go to tests, choose the chi-square goodness of fit test. How many degrees of freedom? Good, 3 in this case. There we go. Our chi-square value is 11.2, and our p-value is 0.017. Sorry, 0.0107. So what's our conclusion here? Good. Reject H and L in favor of HA. We have significant evidence that NHL birthdays are not uniformly distributed. And then again, if we wanted to do a follow-up analysis, it's pretty easy to do just from observed and expected counts. Which one is furthest? Which one's the largest contributor to our chi-square test statistic? So that one had 8 fewer players born to it, right? But January through March had 12 more players born to it, which was what Malcolm Gladwell was saying, right? You're more likely to go to the NHL if you're born in January because then you're going to be an older player growing up. It's true for a lot of things. Which is sort of the opposite of intuition, especially working at a school. Parents often are, especially in math, parents want their kids to be in the highest math class at the youngest level. Which, like, this is, you know, there's evidence that that is not going to benefit them because they're going to struggle a little bit more. They're not as academically mature, and then that's going to put them off math. So my solution as department chair is just, I'm going to rename every course below calculus pre-calculus. So like math 5 will be pre-calculus 1. And then maybe that'll appease the parents.
That's like pre-calculus too.
Yeah.
Like,